Assalamu alaikum. In this video, let us look about linear accelerator or otherwise known as LINAC, linear accelerator. The linear accelerator, this is used to study about fundamental particle, to study about fundamental particle. So, used to study about fundamental particle. So already we have learned that these fundamental particles only occur during very high speed collisions. So this linear accelerator or the particle accelerator, they are used to increase the speed or the energy of that particle and then make collisions to study about them. So let's look how this particle accelerator works. So this linear accelerator, it is constructed using conducting tubes. And these conducting tubes, they are connected to a high frequency voltage source. So it is connected to a high frequency voltage source. Now we know as this is an alternating voltage source, the potential will keep on alternating. Now let's consider the total time period for this wave to be t. So during a half cycle for t by 2 time, let's say this is positive and this terminal is negative. So the first tube becomes positively has a positive potential, and then the third tube, so the third tube and the last tube according to this diagram. Then the second tube is negatively charged and the fourth tube is negatively charged. Now it's quite interesting. Look, the alternating tubes, they have the opposite potential. The alternating tubes have opposite potential. So what is the reason? Let's consider two tubes. So this is the first tube and the second tube. So the first tube, it is positively charged and the second tube is negatively charged. So there is a potential difference between these two tubes, hence a electric field is set up between them. How about the electric field inside a tube? Do we have an electric field? Let's think about that. Now in electric field we have already learned that in a conducting or in a conductor the potential is same everywhere. We call them to be an equipotential surface. They are having an equipotential surface. When they have an equipotential surface, the voltage throughout them is same. Hence, the potential difference is zero. If the potential difference is zero, then the electric field is zero. So, electric field within the tube is zero. That means we know that on a charge, if we want to accelerate a mass, okay, let's think about a proton. The proton has certain mass m, and I want to accelerate that proton, so I need a force. How is this force obtained? This is the electric force eq. So the acceleration totally depends on the electric field. If there is an electric field, we have an acceleration. If electric field is zero, then the acceleration is zero. So within the tube, the electric field is zero, acceleration is zero. Within a tube, this proton or that charge is going to move with a uniform velocity. And then between two tubes, we have a potential difference. Therefore, the electric field is not zero and acceleration is not zero. We are going to have an acceleration between two tubes. So here we have an acceleration when the particle has moved through this tube. At each and every gap between two tubes, it is going to get accelerated. Potential is going to change. The tube which was positive, after t by 2 time it becomes negative. Now let's see why this is important. So if we consider the first tube and the second tube, I'll draw the third tube also. So here, from time period t is equal to 0 to t is equal to t by 2, we have the first tube at a positive potential. The first tube is at positive potential, the second is at negative, and the third again is at positive. Now, if I mark the electric field here is in this direction, and between these two tubes, we have the electric field in the opposite direction. What will be the case for the time period t is equal to t by 2 to t is equal to capital T? So, the polarities will reverse, right? Now, the first tube becomes negatively charged, negative potential. The first tube becomes has a negative potential. The second tube has a positive potential, and the third tube now has a negative potential. So, if I mark the electric field are in the opposite directions. So, let's look how this particle gets accelerated. Now we have a proton. So this proton, let's say it leaves this tube at a certain time and with a certain speed v1. Now it has a certain speed v1. In this region, so this is during the time. Now we are talking about a situation where we have the positive potential for the first tube. So, in between this region, in between this separation, the particle undergoes an acceleration. So, this particle now obtains a velocity v2, and we know within this tube there is no acceleration. So, it will continue with speed v2. Now, if the particle leaves this tube, if the particle leaves this tube in this situation, will it get accelerated? No, it will get decelerated because this electric field is in the opposite direction. But what are we trying to do? We are trying to have a acceleration, a continuous acceleration. So, how can this be achieved? What we have to do is So, how can this be achieved? What we can do, what we can do is, let's say the time of this is going to be t naught. T by 2 is equal to t naught. Now, We know what is the speed of this particle v1, and we also can calculate what is the speed of this particle after getting accelerated. So this particle will take some time t naught to travel between where it started and to this end of this tube. If this time t naught matches t by 2, what will happen? It's simple. That is, when this particle is about to leave the second tube, now the polarities will reverse. So when the particle is over here, the polarities reverse. So now this particle again undergoes an acceleration, and this time the next tube, the fourth tube, it will be at a positive potential. Okay, so if we mark the electric field, it is like this, and now we match the same time t naught. So every t naught time, so this particle will take time t naught to travel from end of this tube to end of this tube. So again, when the particle is just about to leave, the polarities will reverse. The polarities will reverse. So when about to leave, again the polarities reverse. The particle will undergo an acceleration. So if you observe one thing, each and every time until the electric field is not in the direction of our desire, or until the electric field comes to the direction we want, we try to keep this particle within the tube. Okay, so when the direction of the electric field is opposite, we keep the particle inside the tube, because there is no acceleration or deceleration. It moves with uniform velocity, and when the electric field is in the right direction, the particle leaves, and again it will continue within the next tube until the electric field turns to the desired direction for the next tube. So here, the acceleration only occurs each and every half cycle. So let's make a note of what we discussed up to now. First, the linear accelerator is made up of conducting tubes connected to an alternating voltage source. Second, the alternating source is connected such that the adjacent tubes the adjacent tubes are at opposite potentials. So how can we achieve this? By connecting the positive and the negative terminal of the supply uh, to alternative tubes. This is achieved. This is achieved by connecting positive and negative of the supply, or let's say not the positive and negative, let's say the opposite terminals. This is achieved by connecting the opposite terminals of the supply alternatively. The acceleration of the particle only occurs in between two tubes, not 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 within the tube. What is the reason? Since electric field is equal to 0. Uh, since delta V is equal 0, and this in return E is equal 0. So if I draw the tube, let's say when the particle is here, there is no potential difference. Delta V is equal 0. Therefore, acceleration is 0. And when the particle is in between these two, there's an acceleration. Draw it in two separate diagrams. There's an acceleration. Next point, when the positive charge and when the positive charge and the electric field uh, in desired or in same direction, the particle accelerate. The particle accelerate. When they are in the opposite direction, when they are in opposite direction, the particle continues to move inside the tube inside the tube until the electric field is in desired direction. Now let's say the gap between all these tube is the same. Okay, the first and the second tube, in every tube the gap is same. Therefore, again the potential difference is also same. So let's say the potential difference between these two is delta V. then the potential difference between these two tubes is also going to be delta V, because we are connected to the same voltage source. So that says the electric field strength is also the same. Now we know that work done is force into distance, and here the force done is EQ into D. So the work done between each and every gap is the same, because all of these are the same. And we also have another equation for work done, that is the change of kinetic energy. And in case of electric field, or in case of electricity and all, we can give kinetic energy in terms of electron volt also. So we know that the charge of a proton is Q, and let's say the potential difference is V, then change of kinetic energy is equal QV. So we can say the energy gain by the particle during each half cycle is delta kinetic energy, which is equal to QV. So here, let's say the particle started with zero velocity. Here, the kinetic energy gained is QV. When passing the second tube, it gains an energy of 2QV. So, when passing n number of tubes, the energy gain, the energy of particle after passing n number of tubes is n times QV. Hope the idea is clear. Let's look an example to understand much better. So let's look at this example. Here we have a proton of kinetic energy 1 kilo electron volt entering the first tube of the linear accelerator. If the proton comes out of the first tube in time 1 millisecond, what is the length of the tube? So we know that kinetic energy is equal half mv squared. Kinetic energy is given. Using that, we can find the velocity. So that's the first thing you have to do. And for this video, I'll tell the velocity. That's uh, 4.38 into 10 to the power 5 meter per second. So what is the length of the tube? Now remember, when this particle enters this tube, it travels with a uniform speed. There is no acceleration within the tube. So, the length of the tube, by applying S equal ut plus half at squared, acceleration is 0, therefore S is equal to ut. Let's consider the length of the tube to be x, then the speed is 4.38 into 10 to the power 5, and time is 1 into 10 to the minus 6. So we get the length to be uh, 0.438 meters. So in centimeters, it is 43.8 centimeters. So the length of this tube has to be 43.8 centimeter. So that's the first question. And the second, if the potential difference between this tube and the second tube is 3000 volt, what is the energy of the proton when it enters the second tube? So, the second question, this is our first tube, and here we have our second tube. In between these two tubes, we will have acceleration, or work is done on that particle, where the work done can be given by delta kinetic energy, which is equal QV. Now, this is a proton, therefore, the charge of a proton is same as the charge of an electron, and the potential difference is 3000, or this could be written as it's 3 kilo electron volt. What the change in kinetic energy? But initially it has a kinetic energy of 1 kilo electron volt. So when it is entering the second tube, the kinetic energy becomes 4 kilo electron volt. 4 kilo electron volt. Third, for the proton to travel for another period of 1 microsecond in the second tube, what should be the length of the tube? Now we know until the electric field comes to a desired direction, the particle has to travel inside the second tube. Until the electric field changes to this direction between the second and the third tube, the particle is required to travel inside this tube. So, we know that kinetic energy is equal half mv square. So, half m is a constant, then v square is proportional to kinetic energy, or v is proportional to root of kinetic energy. So, we had v1 proportional to root of 1 and v2 proportional to root of 4. So v1 over v2 is equal 1 over 2. So v2 is twice of v1. That's 2 times of 4.38. We calculate, we get 8.76 meter per second. So again, it travels for a period of 1 microsecond. Hence, the length becomes 87.6 centimeters, and the first tube was 43.8 centimeters. So it's clear that the length of the tube has to keep on increasing to accommodate that particle within the tube until uh, the electric field changes to the desired direction. So here I think we missed a note. Here we can include that the length of, before the example, the length of alternating or the adjacent conducting tube increases to accommodate the particle inside the tube until electric field electric field is in desired direction. Hope you're okay with the example. And next, let us look at a circular accelerator. So the circular accelerator, it works same as the linear accelerator. The only difference is it goes in a somewhat circular path. Actually, it's not circular, but somewhat circular path. Here also, the particle is accelerated in between few points. Okay, and in the remaining positions, they are just deflected so as to correctly pass through these potential differences. So we know when there's a potential difference, the particle will get accelerated. So now the difference between the linear accelerator and the circular accelerator is this path. How can we achieve this path? This path is achieved using magnets. So how we can use magnets to achieve this? Let's look. We know that in a region of magnetic field, so in a region of magnetic field, if we have a particle, let's say a positively charged particle is projected into this with velocity v, then it will undergo a circular motion. So here, according to this Fleming's left hand rule, force is upward. Now this will undergo a circular motion. So we use this property or this character to deflect the particle. It's like when this particle is moving in this direction, here it is a magnetic region or there's a magnetic flux. What this does is this brings this particle into a circular motion. So this is a small arc and this particle is deflected. So the particle which was supposed to move in this direction, now it is deflected by an angle theta. So if I draw, like, let's look at this. So now we have a region, magnetic region with dot. So when this particle is entering over here, this is the direction of the particle v, and magnetic field is out of the screen. So if we mark the direction of force, it's towards the center. Now this undergoes a circular motion. So these dotted red lines show the circular path or the path taken by this particle. And if I draw the center, center for this circle, this line, and this is going to be perpendicular. Okay. Now let this angle be theta, and the distance of this magnetic region, let it be s. So this is also going to be s. If I draw the deflection, I'll try to find what is the angle of the deflection. So uh, we know a quadrilateral that will add up to 360 if opposite sides add up to 180, because this is 90 and 90, these opposite sides have to add up to 180. So if this angle over here is theta, if this is theta, this is 180 minus theta. This is a straight line, hence this angle is theta, and that's the deflection. So now let's try to find an equation for this deflection. So first I will try to obtain a relationship for this magnetic field. No, let's try to get a relationship for theta. So look, if I connect these 2 points, now it becomes a triangle, right? and I'll connect this side, the centers. Now it becomes a right angle triangle. So theta by 2 sine opposite over, no. So if I consider this angle, it's theta by 2, opposite is s by 2, and adjacent is r. So sine theta by 2 is equal opposite s by 2 over r, hypotenuse. So we have sine theta by 2 is equal s over 2r. So theta by 2 is equal sine inverse s over 2r. So theta is equal 2 times sine inverse s over 2r. So this is the angle of deflection. By this angle only deflection is measured. So look, this S is going to be a constant, the region. Next we have R. R depends on the magnetic field. Let's see how. So we know the equation for magnetic particle in a magnetic field, that is given by M. F is equal to BQV, F is equal to BQV, and as it is a circular motion, it is mv squared over R. So R is given by mv over BQ. So now uh, M and Q is constant. M and Q is anyways constant, but the velocity when it is going in a circle, when it is going in a circle, it is going to keep on increasing, right? When the velocity increases, then r will change. If r changes, angle theta will change. If angle theta changes, then this particle cannot exactly go through this potential difference. So according to the speed, b has to be varied. According to the speed, b has to be varied so that this angle theta remains the same, and every time the particle will go through the same potential difference. So in simple, that is how the uh, circular accelerator works. So here you have to take a note about, just try to get this diagram printed and show using this equation how the deflection occurs, and then so you can tell how it is deflected, and finally using this equation you can write a statement how that particle is always maintained within this same path. Okay, so that's all about this circular accelerator. I hope you all got the idea. If you all have any doubt, let me know. Assalamu alaikum.